draw the truth table for XOR. So let's say that we have this vector of booleans, which is big X. Let's define that, and big X is defined to be x1, x2. And so we have x1, we have, oh, so this is 0, this is 0, this is 1, this is 1, and we want to separate them with a linear model, and we can, and basically it's mathematically impossible to do this. The mathematical proof for this is not very difficult, so I won't go to it, but basically, so suppose that, you know, there's obviously many ways to do it. A geometric way would be is by taking the area of the triangle using vector calculus methods, and you'll find that if it's on one side, on the left side typically, then it's positive. If it's on the right side, it's negative depending on how you do it. So you define that function, and then you have a line y equals mx plus b, any line, and you'll see that with any arbitrarily selected line, it is not separable. So that was just a side thing. That was just me geeking out. We want to figure out a way to use a linear model to separate this. And the way to do it is that if we are allowed to use nonlinear features, then we can devise a linear model to separate the XOR function. And what we're essentially doing is feature engineering. So take x1, x2, but now we're going to say, how about x1 and x2, or x1 times x2, either way doesn't matter. So what we're really doing here is we're taking our domain and transforming it from z2 to z2 3. That's what's happening here. And so our domain is literally just 4 elements. So it's not like we're ever worried, like this is just kind of a toy model for theoretical thinking and to introduce like the power of nonlinear features and such, right? So it's not like we're worried about doing training or testing data or anything like that, or validation sets, nothing like that. It's purely mathematical. 0, 0 is 0, 0, 1 is 0, 1, 0 is 0, and 1, 1 is 1. Great. This is our new data set. And what we're really doing is we're taking this data set, we're putting it through this feature pipeline, and then we're tossing it into the model, which doesn't do anything because we're going to hard code the weights anyway, right? So what we're now imagining based off our new data set is this. So here's 0, 0, 0. Here's 0, 1, 0. Here's 1, 0, 0. And here's 1, 1, 1. Now this is linearly separable. And the way we're going to do this is, let's take a vector where we want to find, and you could do this by saying, well, if it's on the plane that's one way or the other, or you can literally separate the two classes in this case by adding a very small bias. But I'm just going to do this. I'm going to find the plane on which these 2 points lie. So we're going to create a vector from 0 to 1 to the 1 vector, right? So we have this normal dot 1, and because it's on the plane, it should be equal to 0. That means that if we express this out, that means we have x plus y plus z equals 0. But we have to take into consideration that what we want from our machine learning model is that the black points are going to be separated. So we don't want these to be 0 also. So we want to take note. And this is in the x component, of our basis, we worry that, x1, for this case, this is one data point, right? This is row major, this is one data point. There's a 1 here, 0 everywhere else. So if x is 1 here, then this dotting it with this is going to become 0 also, which we don't want. So the equation we're trying to solve is x is not equal to 0, y is not equal to 0. This is pretty easy to do. We just keep in mind that we can't have these, but we have plenty other choices, right? So let's say that actually, let's say negative. Say z is equal to 1. So that's negative 1/2 plus negative 1/2 is negative 1 plus 1 is 0. So we have satisfied the constraints of all of them because these are not 0. So this is all satisfied. So then the normal vector, which if I want to put it in standard form to represent this plane, the normal vector is going to be negative 1/2, negative 1/2, 1, and yeah, and so this is 1 divided by square root of 2, so that this becomes unit. And these are also our weights for the model. And by the constraints that we have chosen, by definition, we know that these two lie on the plane. The two zeros lie on the plane. Let's say the 2 0 data points lie on the plane, and the 1 data points do not lie in the plane. But we can check exhaustively so that we can say our bias is 0. So is this 0 vector? So for example, so let's write out our model, right? And this is 1x3. This, yeah. So that's the transformation that the model applies. Now our inference function is going to be basically it's this. Okay, it's if it's 0 if f of x is 0, 1 otherwise. Now the reason why I can do this is that XOR is literally just 4 elements. Our data set is 4 elements. We have exhausted the entire universe of elements. So when we pass any x in any arbitrarily selected x in the universe of data, it's going to be either 0 or 1 based on this. And there will be no mistakes because we have mathematically proven that this model works, because we can literally do exhaustion by going point by point. We just saw that, okay, 0, 0, 0, what does that do? Based on this, that makes it 0, so this is going to be a 0. So let's just even do this. That's going to be a 0. How about 0, 1, 0? Well, that's negative 1/2, so that's going to be a 1. This is also negative 1/2, that's going to be a 1. And this is 0 because it lies on the plane, right? So this is going to be a 0. So this model works. This is our model. We have we're just hard coding the weights. There is no training process here. So maybe the plane will look something like this, right? Where the zeros lie on the plane, and it's pointing like this. So this is the normal to the plane. And these 3 points are on the xy plane, but this plane is kind of tilted upwards like that. So that's the linear boundary. By definition, our model is linear because it's a linear combination. But these features, of course, are nonlinear. But right, this shows that the XOR function can be separated with a linear model, provided you are allowed to do feature engineering to generate nonlinear features.